Man, I don't know how today is going to go. I just have a really sinking feeling about it, you know? I feel totally drained. Oh, oh. That could explain it. All these puns, I know you're thinking, like, don't faucet, Mr. Young. Force it? Faucet? Okay. Why don't you guys let that sink in? And we'll do a little calculus today, all right? I just want to make sure. Oh, it's not telling me to tap on the screen here. It's saying there's a water tap on the screen. That's some tricky stuff. The smartboard got me on that one. And looks like there's a picture under here. Oh, that reminds me. We want to make sure later in May that we celebrate the Cinco de Mayo. Because that went a lot of work trying to find that picture. So I hope you guys appreciate that. And no, I'm not done. I got one more, okay? Do you want to know how you can tell if an ant is male or female? Well, you throw an ant in some water, and if it sinks, it's female. And if it doesn't sink, boy ant. Because float. All right. We didn't get to do one of these last time, so I'll do one today. It's a nice practice of our partial fraction procedure, and this is how fast I hope you guys are eventually able to go through this. So I'm going to jump right to my setup step, which is the ABs. This is already factored for me. So A over x plus 2, B over x plus 1 dx. And then we jump right to the only algebraic step I'm asking you guys to do. Switch the denominators. If you still don't understand why that's happening, make sure you guys go back and watch the partial fraction video. And we want it equal to the numerator, 2x. And then you guys can do this stuff in your head. I have no problem at all. So I know I'm going to plug in -1 here in order to solve for b. -1 plus 2 is going to give me 1. This is going to be -2. When I divide by 1, b will equal -2. And I'll do the same thing for a. Plug in -2 here. -2 plus 1 is -1. -2 times 2 is -4. Divided by -1, I get a +4. So I'm looking for an ln with a +4, and that's going to go with x plus 2. I need a -2. That's going to go with x plus 1. There are no chain rules to this. There's no negative x's. There's no coefficients in front of the x's. So I feel pretty good about this being our answer. Look at every cruel possible combination that's in here. This one especially is really nasty. I think that's kind of mean, but so be it. All right, so there's a bunch of little wrinkles that go along with these partial fraction antiderivatives. And here's the first one. So what we run into is a top-heavy antiderivative. The nice thing about these is you can't mistake these for a u sub. You don't even need to bother. Because even though these are 1 degree away, you can never have du in the denominator. There's no way to escape that. There's no way to get du from out underneath the denominator. So I know I'm looking for a different strategy. I know this is not a u sub. And I do notice that this factors. So I'm leaning towards partial fractions. But the problem is the denominator is too big. So if I jump into a partial fraction right now, I have this giant piece in the numerator that's going to morph and disappear into my partial fraction. I need to find what part of this isn't part of the fraction. So how do I do that? I'm going to use division. This says divide this by this, 2x to the third divided by. So we're going to actually do that division. We're going to do 2x to the third divided by, and we're going to divide x squared minus 4 into this. We have to whittle this down so that at least we have a bottom-heavy fraction. Otherwise we can't apply partial fractions. We're going to lose the piece that's not in the remainder, which we'll show in our long division here. Now remember what you guys did in Algebra 2. I know it's been a while, but technically all of this is here, and there's a 0x plus a 0. All of that is really there. That's going to be helpful as I do the long division. So x squared times what will give me 2x to the third? Well, 2x times x squared gives me 2x to the third, but I also have to multiply this by 2x. So I'll have a minus 8x here. Now, this term became irrelevant. I didn't need this term anymore, so I'm just going to cross it off and use this one. And now remember, just like doing the long division problem from back in the day, if I did say 71 divided by 6, 6 would go into this once, bring the 6 down, and I'd subtract. I'd get 1, carry the 1, and then I'd do it again. 6 goes into this once, so I bring down the 6, subtract, and I end up with 5. And this is my remainder. So my answer to this problem would be 11 and 5/6. That would be my answer to this division problem. Of course, we could make it improper if we wanted to, so we're going to do the exact same thing over here. So I'm taking this divisor, subtracting this whole thing. So 2x cubed minus 2x cubed, this has to cancel. You've done your long division incorrectly, and it does. And then we've got 0 minus negative 8, which is a positive 8x. And now I can already see I'm finished. I can't divide this into this. There's nothing I can multiply to make this happen. So this is my remainder, and my long division is finished. So now the tricky part, the place where students usually get lost, we have to do our rewrite. So we are going to rewrite this. I need a new integral. Well, now this is a whole value piece. It's not over a fraction. This was just 11. This is just 2x. Plus, well, now I need to account for that 5/6. There's 11 and 5/6. So we have 2x, and what else do we have? We want our remainder out of our divisor. Our remainder out of our divisor. So 5/6, so x, or 8x over x squared minus 4 dx. So there is our new integral. Now we have this whole value piece. We've removed that, and now I see a bottom-heavy fraction that factors. Now at this point, don't go diving into partial fractions. What should you always check now? We're going to check a u sub, just to be safe. Always check u sub, see if it's easier. So if I make u x squared minus 4, then du would be 2x dx. And what do you know? I don't need to use partial fractions here. It would work just fine, but this is so much simpler to do a u sub on this. So I'm going to treat this as two separate integrals. This is a very simple one. Plus, here, I'm just doing a u sub on this. I've got my x squared minus 4 over 8x dx, and I can see that this is going to work out fine. I just need to multiply du by 4, giving me a perfect 8x dx. And I never needed to do a partial fraction. Just because this factors doesn't mean it's a partial fraction. So we can finish this really, really quick. The antiderivative of 2x is, of course, x squared plus, what am I going to end up with here? Well, I'm going to end up with a 4 in front of this thing, and then I'm going to have a perfect match and a perfect match. So I've got 1 over u du. There's where my ln comes from. I end up with the, 4 times the ln of x squared minus 4 plus c. Now let's say you accidentally did a partial fraction here. This is not what the answer will look like. You'll get x squared, and then this piece is going to be broken up. You're going to have an x plus 2, you're going to have an x minus 2, but if you use the property of logs, there'll be addition between the two logs, and you can multiply them together and get back to this spot anyway. So they won't look identical at first, but they are. And there is our perfect antiderivative. So, we're looking at top-heavy fractions. Here is a little bit of practice, and we'll have to decipher through what's partial fractions, what's u sub. All right, this one's pretty obvious that it's top-heavy. That one's less obvious, but certainly the same thing minus 9 is going to be smaller than the same thing minus 6. So that is top-heavy. That would require long division. So let's do some division. I'm going to talk through both of these because I know it's been a long, long time since we've done long division. So I want 3x to the 4th. I'm going to write out all my terms here just to be careful. Plus 0x plus 1, 0. Wow, good thinking, yeah. And oh no, that was right, 1. Losing my brain. Got this really sinking feeling, like I said. All right, there we go. There's my numerator dividing by this guy, and off we go. So it looks like I need 3x squared to make this true. And now I get 3x to the 4th. There won't be any x cubed terms. And 3x squared times this, I'll have minus 3x squared as I multiply that through. And I need to subtract all of this. This minus this cancels as it's supposed to. 0 minus negative 3 is going to give us positive 3x squared. And now how many times will that go into that? 3 times. So I add 3. And now what do I get? I get 3x squared minus 3. So I won't need this term. The plus 1 comes down. And I'm subtracting this quantity. These have to cancel or you did something wrong. And 1 minus negative 3 is 4. And there's your remainder. So we rewrite this. And hopefully you guys can already see an emphasis on having your signs correct. One little sign error here, and this is the wrong remainder, which gives you the wrong partial fraction, which makes the entire antiderivative incorrect. So I'm going to rewrite this. Both of these pieces are whole number pieces, plus 3, plus my remainder over my divisor. So 4 over x squared minus 1 dx. And now I know the antiderivative of these two things. Those are just simple power rules. This is the one I'm going to focus on. So I'm going to bring this down here, and I need to do a partial fraction on just that guy. So I'm going to do this, 4 over x squared minus 1 dx. And I got to do all the a's and b's and all that wonderful algebra. But by now we're pretty quick with this, right? So we're going to do a over x plus 1, b over x minus 1. That's how this factors. Rewriting this dx. There's my setup step. Here's my algebra step. By the way, it doesn't matter which place you put these in, it's going to work out regardless. Bx plus 1, and then I need this equal to 4. So if I choose 1, this goes away, and I'll get 2b equals 4. So b equals 2. If I choose negative 1, this goes away. I'll get negative 2a equals 4. So a is going to equal negative 2. And now I've got one more step. So my new integral is now negative 2x plus 1, and then of course 2x minus 1 dx. You've got some options with your logarithms here. If you guys want to combine logs, turn it into a fraction and change the order of your subtraction, do whatever you want, but I'm going to write it the simple way, right? So minus 2 ln of x plus 1, 2 ln x minus 1 plus c, and don't forget, we left these guys off, so we have to bring these guys back. The antiderivative of 3x squared is x cubed. The antiderivative of 3 is 3x. So my final answer here is x cubed plus 3x minus all of our ln's. So I antiderived this piece, and this was a partial fraction. And there is my final antiderivative. Wasn't that fun? Of course it was. So fun, in fact, we'll do another one. The division should be really simple in this case, dividing just barely larger by just barely smaller. And I know it's only going to go in once. I'm not even going to bother with the 0x term. I can see that I'm not going to have that problem. So I get x squared minus 9. But remember, I'm subtracting this. So these cancel. They have to. Negative 6 minus negative 9 is 3. All right, that's my remainder. So let's do our rewrite. And be very careful with your signs, of course. In this case, not too much of an issue. We now have 1. That's our whole number value. This is positive 3, so plus 3 over x squared minus 9 dx. And we're just going to do a partial fraction on this piece right here. So I'm going to jump right into that. A over x plus 3, b over x minus 3. There's my setup step for that. We'll leave this guy off. And now let's try to do some really fast algebra here so we don't waste a lot of time. So I know I want x minus 3, reverse my denominators. Oh, come on, you stinker. Go back. Smart board, we were just starting to get along today. There we go. Equals what? Equals your original numerator of 3, at least half of it. A good half anyway. And now I'm going to plug in 3. That's going to give me 6. When I divide b, it's going to equal 3 over 6, which is a half. When I choose negative 3, I'm going to get negative 6. So I'm going to get a negative half, 3 over negative 6. And now I'm going to jump right to my answer. So a will be a negative half. I'll jump right to my ln. ln of x plus 3. b is positive half. ln of x minus 3. Don't forget the plus c. And, very cautious, but don't forget your whole number term. The antiderivative of 1 dx is x. And there is our final answer right there. So if you see a top-heavy fraction, there's a very good chance you're doing some polynomial division. There's a small chance you won't. I'll give you guys some cases where you wouldn't. But be very careful when you automatically assume a strategy. So here are quite a few. Here's the ones I don't want you guys to be fooled on. As has been my routine, we just did those. So avoid those. We already know. Thank you. We already did those two. Here's a couple where I don't want you guys to be fooled. Notice here, this is top heavy. U sub's not going to work. Many of you would think, well, I have to do long division here. Sure, you could do long division here. It will work just fine. But notice you can just split this apart, and you can do 4x to the third over x squared plus 1 over x squared dx. And now these are both power rules. This just simplifies really nicely. The x's cancel, and you're left with 4x dx, which is just 2x squared. And then here, this is a power rule, not a natural log, right? So this goes up to -1, and we need -1 to cancel that. So let's just make it a little bit cleaner and say this is minus 1 over x plus c. You would have gotten that either way. Wouldn't have mattered if you did long division or not, but if you notice the separation here, it's much faster than having to go through any long division. And don't be fooled here. This is bottom heavy, 1, but it's addition, so this does not factor. X squared minus 4 factors, x squared plus 4 does not factor. This is an arctangent, and just for fun, let's go through that. We'd have to pull out the 4 from the bottom, which is a 1/4. That would leave us with 1 over 1 plus x squared over 4 dx. And now as I rewrite that, 1 over 1 plus, well, x over 2 squared. That's going to give me my original piece. So this is a little baby u sub. Every one of these is 100% of the time, every time. du equals 1/2, and we don't want 1/2. We have to have 1 equals 1 dx. So the 2 comes out front. 2 times a 4th is a 1/2. I know the antiderivative of this is arctangent of u, and u is right there. X over 2 plus c. Not everything is a partial fraction. Not everything requires long division. All right, so if you see a top-heavy fraction, you're going to long divide. It's only really going to be worth your while if the bottom factors, but you can always long divide if it's top-heavy. All right, another little twist here. So the twists, I'm not going to make you guys finish the problem from start to finish, but I will ask you when the twist applies. So I noticed this and I noticed this factors, so I'm leaning towards partial fraction. I know a u sub's not going to work. The derivative of this would be something squared, and that fails, which is the first thing you should try every time, but it doesn't work. So what does the factored form of this look like? Well, we end up with x plus 12 over, I can take an x out of this, and then I'm going to be left with what? I'll have x times x squared plus 4x plus 4. And now that factors into x plus 2 times x plus 2. This is a very unique case. If we're trying to set up partial fractions, each fraction that we're trying to set up has to be unique. It has to be distinct. In this case, there'd be 3 partial fractions. There's a 3rd degree polynomial on the bottom. There's 3 different factors, but they're not different factors. So the wrong way to do this is to set up the following. If I did a plus b plus c, certainly my first factor is x, that's not going to change. X plus 2 is not going to change, but I can't use x plus 2 again. There'd be no difference between these 2 fractions at all. This is not a distinct factor of this expression. Just like having, imagine you had 3 over 12. I can factor 12 into 3 times 2 times 2, but each of these 2's are not a unique factor of 12, they're the same factor of 12. However, 3 times 4, 4 is a unique factor of 12. It goes into 12 3 times. 2 goes into 12 6 times. Each of these 2's go into 12 6 times. So what we need is a unique factor here. So I don't want another x plus 2. What I want instead, my correct partial fractions, is going to relate back to how I used that 4 up there. I'm still going to use a over x. I'm still going to use b over x plus 2. But my next unique factor would be the combination of these 2 things. In this case, x plus 2 quantity squared. This would be a unique factor of this product. Once we have this set up, It's the same as every other problem. We go through the algebra, rewrite our integral, blah, blah, blah. All right, so here it is. Set up my algebra. So let's go through the algebra really quick. Now, there's 3 partial fractions, so I have to multiply by the other 2 denominators. So you kind of have to think through this, but this denominator would need an x plus 2 squared. This would need an x and another x plus 2. And this would need an x to make all of these common. So if you guys understand the algebra done there, I'm going to skip past that. So I would need a times the part that's missing in order to make this common denominator. So I would need x plus 2 squared next to a, plus b is missing an x and another x plus 2, and plus c is only missing, it's got these 2 things, it's missing this thing. So c would need to be multiplied by x over x, and we're going to say this is equivalent to our numerator of x plus 12. And now we do all the same things that we used to do. Negative 2 is going to save us a lot of stress here. If I choose x equals negative 2, this is going to be gone, this is going to be gone, and I'm left with negative 2c equals 10. If negative 2c equals 10, then c equals negative 5. And then of course x equals 0 seems to be another logical choice. If x equals 0, this is gone, and I'm going to get 2 squared. 0 plus 2 squared is 4a equals 12. So a equals 3. And now what do you do, Mr. Young? We've already used 0 and we've already used negative 2. Yes, but we have a and we have c now. So I can rewrite my equation, plugging these 2 things in. If I plug 3 in for a, I'm going to have 3 x plus 2 squared plus b, I don't know that, that's what I'm trying to find, plus, well this is a negative 5x equals x plus 12. Well, this is an equation I can actually solve. Is this tedious? It's just an algebra equation. If we started class with this, you'd be wishing you could do simple algebra like this, right? So let's start to solve this. I'm going to do the algebra first, and then I'll start to choose an x number, because I can choose whatever I want. I chose negative 2, I chose 0, I can choose 100. Doesn't matter what I choose. But let's clean this up first. So I'm going to get 3x squared. 2x plus 2x is 4x, so I'll have 12x plus 4 times 3 is 12. And then I'm going to have, well here's where it's going to get a little bit tricky. I'm going to have bx squared plus 2bx, and then I'm going to throw my minus 5x over here. So cleaning all of that up, what do I get? 12x minus 5x is 7x. So I've got 3x squared plus 7x plus 12. And then I'll add on these terms over here. And this is supposed to equal x plus 12. One more step of algebra later. Let's just subtract this. Doesn't really matter what side I do this on, so I'm going to subtract this x. This will become a 6x. The 12's I can see cancel. And I've got 0 equals 3x squared plus 6x plus bx squared plus 2bx. And at this point, it doesn't really matter what you choose. Let's just let x equal a very simple number of 1. We've already used these 2, so I'm going to pick a different one. And we get 0 equals 3 plus 6 plus b, 1 squared is 1, plus 2b. And it looks like this is going to work out real nice. I'm going to get 9, I'll subtract it. Negative 9 equals 3b. And it took us a long time. we had a lot of options here. I'm trying to do it a little bit longer way so that it makes sense, but b equals negative 3. So check, check, and check. And now we can actually go back and finish our antiderivative. I'm not really going to bother rewriting this to save steps, so negative 3, 3, and negative 5. 3, negative 3, and negative 5. Do I have those in the right order? Yes, I do. And now let's be very, very careful with our antiderivative here. This is a simple antiderivative. I get 3 ln of x minus 3 ln of x plus 2. And this is not an ln. This would be a u sub. I would let u equal this. The negative 5 would tag along for the ride. And what I end up with is 1 over u squared. So this piece right here is the same thing as this. And there'd be no chain rule to that because du would just be 1. So the antiderivative of 1 over u squared is negative 1 over u. So I'd end up with plus 5 over u. Regular u is just x plus 2 plus c. And there we go. There's our correct antiderivative. If you type this into an online integral calculator, you'd see this piece and you wouldn't know where this came from if you didn't choose a distinct part. So, when you have a third degree polynomial, you should have 3 variables, but you have to use distinct factors when the same factor shows up twice. And here's the reason why you have to do that. One other little wrinkle, and we'll call it a day. So here we have a factored denominator. Let's check u sub, right? So if I distribute this out, I'm going to get x squared times x is x to the third. The derivative of that will not be that, so it's not a u sub. I already see a factored denominator, but let's set this up wrong. So this is another example of the wrong way to set this up. If I wanted partial fractions, it seems more than reasonable to say, oh, well, I'll just put a over my first factor, and I'll just put b over my second factor. And that's it. Done, right? No, not done. If you're going to use the partial fraction strategy, then you have to treat this as a divisor. The trouble with keeping this piece and a regular b is that that's not how your partial fractions would work out. If you guys notice, b is just a value. This would be an inverse tangent antiderivative, but it's not an inverse tangent antiderivative. If we're following the partial fraction rules, these have to be 1 degree apart. Just like when I set this up over here, even though this quantity was squared, this quantity, this value, was 1 degree apart from my negative 5, which is why I was able to antiderive this as 1 over u squared. So the nuance to this is that I'm actually a degree of separation away from an x squared term. So I have to account for that degree of separation with a missing polynomial piece. That's big fancy terms for I need an expression that represents one term off from something that is squared. So this fraction is just fine. This fraction is a polynomial that is 1 degree away from my denominator. So potentially, these two values exist. Maybe they do, maybe they don't. But I know if I'm going to use partial fractions correctly, this is not just a constant. So there is my correct setup. I don't want this. And now, once again, it's the same as every other problem. You do your algebra, you find your common denominator, etc., etc., etc. All right, so what would my common denominator be in this case? Well, I'd multiply a by x squared plus 1. I would multiply b what is it, Vx plus c times x minus 2, and I would need this to equal x minus 7. And now our choices get a little tricky here, but all we have to do is solve for a, b, and c. So there's no rule that says we have to pick a number that cancels stuff. We were just doing that because it was really convenient for us. So we only get one option here that's convenient. The convenient choice here is, of course, x equals 2. That's a really convenient choice. That makes all of this go away. And what does that leave us with? Well, we'd get 2 squared is 4, 5a, 2 minus 7 is negative 5, so a would equal negative 1. Unfortunately, there's no way to make this 0. This will always be positive. So here's where we really have to dig deeper into some algebra. Since we have a, I can rewrite this now as x minus 7 equals just x squared plus 1, since I know a is 1, and bx plus c times x minus 2. You can play the game all day if you want to, trying to figure out what's another value I can get to cancel something. But at the end of the day, you may just have to solve a system of equations. What do I mean by that? I mean make a couple random choices and then solve for b and c independently. So if you guys want to skip past this part of the video, you can. You're not going to ever have to deal with this in this class, but I want to at least show you how. So if we start to attack this, let's say I choose x equals, I'm just going to pick a really simple number. If I pick 0, I'm not going to get all this to go away. I'm still going to have values remaining. I'm going to have a negative 7 on the left. This is going to be 1. This is going to cancel. I'll have just a c left in here. If I plug 0 into here, I'll have a negative 2c. So I'll have 1, and then here I'll have minus 2c. So 0 is a great choice. It allows me to solve for c. Subtract 1 gives me negative 8. Divide by negative 2 gives me 4. And c equals 4. And now that I have that, I can actually plug it in and solve for the other variable. I'm going to choose x equals 1. So on the left side of the equation, I'm going to get negative 6 equals 1 plus 1 is 2. And now being very careful here, x is 1. So plus, I'm going to have 1b, c is 4, and then x minus 2, I said x is 1, this is going to be negative 1. So I get negative 6 equals 2, and then what do I get here? Distributing that, it'll be minus b minus 4, and now it's easy to solve. Subtract the 2, I get negative 8, add the 4, I get negative 4, divide by negative 1, and I get b also equals 4. So sometimes this can be a real pain in the butt, but it's still just algebra. And now we go back and solve our integral. So our rewrite would look like this. I know my a value, I got that one right away. Negative 1, x minus 2, plus, this is one single fraction. Both of these are 4s. You could take the 4 out if you want to. I'm not going to. So 4x plus 4 over x squared plus 1 dx. And now we can antiderive. Now, the tricky part is, how do we antiderive? Well, now you'd have to attack this fraction. I'm not going to go through all this, it's a waste of the video time, but what would we do? I'd like this to be a u sub, but if I try a u sub on just this piece, du would equal 2x, and there's no way to get that to be 4x plus 4. So what would I do instead? I'd actually have to split this up this is divided by this, and this is divided by this. So I need 4x over x squared plus 1 plus another 4 over x squared plus 1. And notice how this is just going to be an ln, this is going to be a u sub, and this is an inverse tangent. You're right, I shouldn't finish this, we can stop there. But I'll assume that you guys could finish those if you needed to. Don't worry, a problem like this will not be on your test anytime soon. But those of you taking college calculus, you need to see this. All right, so different types of partial fractions variations. Distinct factors, this is very basic. This you will see on the test. What about common factors? Well, you divide this into a over x minus 1 plus b over x minus 1 squared. You will not see this on the test. What if there's a higher degree? Well, then I'd have to split this into a over x minus 1 and bx plus c over x squared plus 1. You will not see this on the test. What if it's top heavy and I have to do long division? Yes, this you will see on the test. So these two things you need to make sure you know how to do. These two things don't worry about for your next exam. I just needed to show you those. So before we conclude, there's all your different types of partial fraction scenarios. Let's go through everything we've done now. We'll start to review really quick. No, I'm not going to do all these. I just want to talk to the method you should be using. I want you to recognize this quickly now. X squared, x. What am I doing here? 1 degree apart. This would be u, this would be du. This is a u sub. X and x. These are not 1 degree apart. There's no escaping that. This is a product rule, which means this is a parts problem. And x squared e to the x, well, this would have to be u. That would not be du. This is also a parts problem. Since this is a higher degree than 1, then we are going to use the table strategy in order to do it. What about round 2? 1 degree away, the derivative of this is this. There's a u sub. This is the reverse. This would eventually derive away, but I can't have du inside of a function, so this is another parts problem. In this case, well, that's the same as that, isn't it? These are the same exact degree. This is a product. This is another parts problem. By the way, since this is so high, probably going to use a table on this guy. And last but not least, x squared cosine of 2x. Well, is that any different than this? I can't have a du trapped inside of here. This is another parts problem, and this would require a table. I guess it wouldn't require it, but I would highly recommend it. So you look at how deceptive some of these things can be. All right, and last little round, look at all these fractions, but by now you guys should be good at recognizing this. Always check u sub first. The derivative of x squared is 2x. We could make that happen. This is a u sub. The derivative of x squared is 2x. That doesn't fit, but this factors. So this is a partial fraction. X squared plus 4 does not factor. We're 1 degree apart, but if I pull this negative out, I've got 1 over x squared plus a number. Ooh, this is an arctan u sub. And the last one, I see addition signs in the numerator. Ooh, this can be split up. This is just a basic rule because I can split this up into x squared over negative x plus 4 over negative x dx. This would be an ln. This simplifies and just becomes a power rule. Boom, done, deal. All right, so the next time I see you, you guys already know about this, but this is your homework. And again, to the 8A kids, I apologize, but you don't have this worksheet on paper. You have to do it in a notebook or on a separate sheet for me. All right, that's it for this lesson. I also, at the end of this, if you guys are interested, we would have done this in class, but we don't have class. But this is a combination of all possible antiderivatives. I really want to try to give you as little advice on these as possible, so you have to figure it out on your own. Every strategy is in play here. Every single one that we've talked about. This is a great start to review for your test. So there is the entire problem set. Leave number 1 up and 2, and then there's number 9 and 10. And on the next slide are all the solutions, all the way through 8. There you guys go, if you want to pause the video, and 9 and 10. None of this is required, you don't have to do any of that, but you do have to do this. That's it. You guys have a good one. I'll see you in person.